Suppose that we have at most m linearly independent vectors in V and that the dimension of V is m. Then suppose we have p linearly independent vectors in V. We can take a basis with m elements because the dimension is m. So at least V is a span of these vectors. So we know that we need at least as much vectors that we can choose independently. So P is smaller than M. Secondly, we need at least M vectors to span V. Well, again, take basis vectors M basis vectors linear independent, and a span formed by Q other elements. Then we know that M is smaller or equal than Q. So which is actually a proof. A proof of C. So compare these two reasonings. We need at least as much proof of C. If vectors V1 to Vm are linear independent, they form a basis for V. Well, take an arbitrary V in V, arbitrary vectors, and now form the m plus 1 tuple of vectors V1 to Vm, and as the last vector V, then according to A, these must be linearly dependent. So there is a redundant vector. There's a redundant vector in this list, and it must be V, since V1 to Vm are linearly independent and cannot be expressed in formal vectors. So V is the redundant vector. So if V is the redundant vector, we may express it as a linear combination of the former one. So V can be written as C1 V1 plus C2 vector V2, etc. until Cm times Vm for some constants, for some scalar C1 till Cm. This reasoning holds basically for any vector in V. So we can, for each vector V, we find these constants such that V is expressed as linear combinations of V1 till Vm, which means that actually the linearly independent vectors in V, V1 to Vm, are actually also spanning the space. So the two conditions for a basis are satisfied, and we find that V1 to Vm form a basis of V. If m vectors V1 to Vm span the linear subspace with dimension mv, then they form a basis for V. Well, how are we showing this? Well, we need to show that V1 to Vm are linearly independent. Since then, the set V1 to Vm would satisfy the conditions set out for a basis. On the contrary, suppose these vectors are not linearly dependent. What happens? Well, if they're not linearly independent, then there is at least one redundant vector in this list. At least one. There can be more, but at least one. So in this list, V1 to Vm, now we remove all redundant ones. Remove all redundant vectors from this list. Then we create a new list. Now we relabel the vectors, and now carry new names, v1 star, v2 star. Now we have k vectors less than m at least. And by removing all redundant vectors we have achieved linear independence of these vectors. Also we know that v is a span of these vectors. Well, why? Well, we removed all redundant vectors. So anything we can make by the vectors v1 star, v2 star until vk star can be made as a linear combination using v1 until vm. So we have a span. V is spanning the space v, and v1 star until vk star are linearly independent. So the conclusion must be that by removing the redundant vectors we have a basis. We've constructed a basis b star. But for this b star we know that the dimension is k. And the dimension k is now smaller than m. But this is contradictory to the fact that the dimension of v was m.